Okay, question 7. Between July and September 2019, renewable energy resources were used to generate more electricity than fossil fuels for the first time in the UK. What does renewable mean? Well, renewable resources are replenished as they are used. So even though we're using them, their stocks are being replenished, built back up again. That's unlike coal, that's unlike oil and unlike gas, which are all finite. We will run out of them. This is what you need to say though. Renewable resources are replenished as they are used. That is the official 1-mark definition. 7.2. Half of the electricity that was generated from renewable energy sources came from wind turbines. The remaining electricity, excluding renewable sources and fossil fuels, was generated from nuclear fuels. Evaluate the use of wind turbines and nuclear power stations for generating electricity. Okay. 6 marks. So they're going to want you to make a number of points here and a number of valid points as well. You could tackle this by going through wind turbine advantages and disadvantages. You could tackle this by, and then following that, going through nuclear fuel advantages and disadvantages. You could do wind turbine and nuclear advantages, and then you could do some disadvantages of both of them, or you could kind of pit them against each other, saying wind turbines are good for this but nuclear fuels are bad for this. That's probably how I'm going to do it, just to give that contrasting opinion. I think it flows quite nicely when you do that, as opposed to having it, this is good, this is good, this is good, this is bad, this is bad, this is bad. But you could get all the marks by doing that, by giving lists of advantages and disadvantages. But it does ask me to evaluate, so it does want me to draw some comparisons here. So what am I going to start with? Well, one of the great differences between nuclear fuels and wind turbines is that nuclear fuel is like a fossil fuel power plant in that you can use it to generate electricity whenever, and it can generate quite a large amount of electricity, or power should I say. On the other hand, wind turbines are dependent on the wind. We don't get a constant supply of power from them. So I'm going to start off with that. I'm going to say nuclear fuels provide, or can be used to provide large amounts of power consistently, i.e. without interruption, consistently and reliably. However, wind turbines are unreliable as they depend upon the weather. Nuclear fuels can be used to provide large amounts of power consistently and reliably. However, wind turbines are unreliable as they depend upon the weather. But, wind turbines produce clean energy. There are no waste products. And by waste products, I might be talking about greenhouse gases. There are no waste products. However, That's annoying. However, nuclear fuels will lead to nuclear waste, which must be stored for a long time. Full stop. Good. So there's two examples of points there that you could make. I'm just setting up as a contrast. You don't have to do that. There are lots of different acceptable points here. Let's go and have a look at some. So notice how this 6 mark is marked. What I'd normally do is I'd read through it once. I'd say, is it a really good answer? Does it make important points or good points? Is it detailed, and do you make a judgment? And then I'd read through it and I'd decide, is it level 1, level 2 or level 3? And then I'd read through it again and decide whether it's 5 or 6 marks, 3 or 4 marks, or 1 or 2 marks, depending on what level you're at. So notice there is a judgment given is required for level 3 answer. You are asked to evaluate and make a decision. These are some of the things you might use to base your evaluation upon. Neither source produces pollutant gases, greenhouse gases, or contributes to global warming. Both require structures to be built, taking up land and impacting on habitats. They're both visually unappealing. Wind farms cause noise pollution. Wind is less reliable. There are no waste products from wind turbines. Nuclear energy can be radioactive or emits radiation threatening to health. There are no transport costs associated with wind power. Many different ways to approach this. You do have access to the mark scheme, so I'll let you have a look through this here, or you can always pause this video and have a quick read through them. So pause now, and if you've not paused, you can pause on the rest down there. I'm going to go back to question 7.4, which is the final question, 7.3, the final question in this paper. Some of the electricity generated from renewable resources came from hydroelectric power stations. Figure 10 shows an example of a hydroelectric power station. So this is all water behind a dam. Electricity is generated when, you can see your dam here, and all of this water is going to pour through, losing its gravitational potential energy, using that, converting it to kinetic energy as it moves, and using that to turn this turbine down here, which turns the generator and creates electricity. But let's go back to this. Electricity is generated when the water flows at speed from the reservoir at the top to the reservoir at the bottom. The flowing water turns turbines that are attached to generators to produce electricity, as we just had a look at. Now, what does it tell us? 1,000 kilograms of water is released from the reservoir. That is a mass. So mass is 1,000 kilograms of water. It travels down the slope at 20 meters per second. Speed or velocity, v, is 20 meters per second. It gives us the gravitational field strength on Earth, G, 9.8 newtons per kilogram. Calculate the height at the top of the reservoir, assuming no energy is transferred to the surroundings. So H equals question mark. Okay. So in order to do this, we are going to need to calculate the height, and we're going to be talking about gravitational potential energy here. To work out gravitational potential energy, it's mass. So I should really write GPE here. Mass times gravitational field strength. That's 9.8, as we have up here, times change in height. and we've got the gravitational field strength. We have got the mass. We're looking for the change in height. We do not have the gravitational potential energy though. So we're going to need to find that energy somehow first. How are you going to do that? Well, we need to make an assumption. In fact, no energy is transferred to the surroundings, so we're going to assume all of the gravitational potential energy the water had up here, as it falls, is converted to kinetic energy. Therefore, the amount of kinetic energy down here is equal to the gravitational potential energy up here. So let's start out by working out the kinetic energy, which is the same as the gravitational potential energy. Kinetic energy, one you have to remember, is half times mass times velocity squared. And that is going to be equal to half times 1,000, because we've got 1,000 kilograms of water, times the velocity squared. There is an easier way to do this, which is a bit more mathsy. I'll do that afterwards. So half times 1,000 squared, half times 1,000 times 20 squared, which is going to be 500 times 400, 200,000 joules. So the water gains 200,000 joules of energy, and now we know that the gravitational potential energy, which is 200,000 joules. 200,000 joules. I'm going to rearrange this for the change in height. Rearranging for this over here. Divide by m times g on both sides. And we get 200,000, substituting my numbers in, over 1,000 times 9.8. Your answer is therefore 200,000 divided by 1,000 times 9.8, which is almost 10,000 but not quite. Your answer therefore is going to be 20.4 meters. There you go. That's one way of doing it. I mentioned there was another slightly more mathsy way of doing it as well. So I'm just going to do this. I'll probably do it in symbols mostly. Now, I said that key relationship at the top was that the gravitational potential energy, perhaps you'd rather I wrote GPE, equals the kinetic energy. Therefore, we can say gravitational potential energy is mass times gravitational field strength times change in height is equal to the kinetic energy, half mv squared. I can cancel something here because m appears on both sides. Let's get rid of, I've crossed out half, I meant to cross out m there. So I've crossed out m on both sides, and I'm left with g delta h, so gravitational field strength times change in height, is equal to half the speed squared. Good. I'm looking for the change in height, so I'm just going to say this. Change in height equals, divide by g on this side and this side, half v squared over g. Put our numbers in. We use half, 0.5 times v, 20 squared, all over 9.8. And this time, so 0.5 times 400 is 200, and 200 divided by 9.8 again gives me my answer of 20.4 meters. So two approaches there. Second one I think is a bit more simplistic, a bit more mathematically simplistic when you look at it, but if you want to do the two full steps, that works as well. Okay, so well done. That's all the questions in this paper completed.